Hello students. So in this series we are going to see some questions on electrostatics potential, potential energy, dipoles and related topics, right? So let us start with these questions. So this question number 1, what it says, if electric potential at the origin is 10 volt, so electric potential at origin is given, right? Then what is the electric potential at x is equal to 2 meter, x is equal to 2 meters. So here there is a graph given. This graph, I hope something is visible. So basically there is a electric field versus distance graph, electric field versus distance graph, and you can see that this is point number 2 at this point, right? What is the electric potential at x is equal to 2 meter? At x is equal to 2 meter, they are asking what is the potential. So how do we say potential? How do we calculate potential from field graph? Field graph. Now note that here electric field versus distance graph is given, right? Let us say this is electric field versus distance r graph. So we know dv is equal to minus e dot dr, e dot dr, and here the x components are given, so we can simply write this as minus ex into dx, right? Otherwise you can write electric field in components: ex I cap, ey j cap, ez k cap, and dr vector also will become dx I cap, dy j cap, dz k cap. Here anyway we have to take only x components, so that is what we are taking here, right? Okay, so now if you take integration of this, integration of dv, what do we get? Minus integration of ex dx. So note that this integration will give area under this graph, area under this graph, and with a minus sign here, so this is change of potential. So they are asking at point 2, so potential of point 2, let us say that is v, minus potential at origin. Origin potential they have given 10 volt. This is minus is equal to, this is area under the graph. Now what is the area under this graph? We have to also take area with proper sign. So if you see here the area that we are interested to calculate, this area up to point 2 we have to take this area. So this area, now let us calculate first. What is that area? That area I am calculating. Remember this is negative area first of all, minus, right, half into base into height. So this base is 2 and this height is also given. So how much this is given? Value is this, right? They have written this minus, so that means it will be negative anyway. So minus half into base, this is 2, into this length or this height, that is 20. So let us calculate that. So from here it comes out as minus 10. Now let us substitute here. So this area is going to be minus 10, minus 10. So from here what do you get? What do you get? V you can calculate as this 10 will go that side, and this 10 this, so that 10 will get cancelled out, or should we add it? Add it, right? This is plus 10 and this minus will go that side, plus 10, plus, right? So 20 volt. So that is the answer. This potential is the potential at point x equal to 2, right? That part is over. Now what is the second part? What is the greatest positive value of the electric potential for points on the x-axis for which x is in between 0 to 6? So in between this 0 to 6, what is the maximum potential they are asking? So note that here this slope, when we have calculated this area, this minus sign is anyway there, and this area is coming negative. So negative is going to give us positive, and this 10 will be going that side. So what are we doing is, we, this minus goes that side, 10, and this minus should become positive, so positive. So basically this minus is coming because of negative area. So negative area is there, then it is going to increase. But if the area become positive, then you have to subtract it. That is what you have to understand. So maximum will come up to this point 3, right? Up to this point 3. So till this much this value will be maximum. After that, because of positive area, it will decrease, right? So we have to make sure that, so we can take area maximum up to this much. So now what is this area? Let us add that area. So half into base into height. So if this graph is symmetric, can we simply double this area, right? Can we double it or not? Because we need to see the graph. So this is not symmetric graph. So let us calculate this area now. So half into this height is 3, base into this height, that value they have given here in the question. How much? 20. So this is going to give us 30. So 30 we need to just add. So the maximum value, this maximum value is coming to be 40. Note that. And this is happening at x is equal to, 3, at x is equal to 3 meters, right? 3 meters. So this is what this question implies. That's a very fundamental question, that area under this graph, field versus x graph, gives us what? It gives negative of change of potential, right? So if the area is negative, it will give change of potential positive. If the area is positive, it will give the change of potential as negative. So you want maximum change of potential positive, so you should consider negative areas, right? Fine. So let us move to the next question. Okay, let us go to question number 2. What this question says: figure shows a graph of, again this question is almost similar to that. The graph is between field and no distance, and this is only along x component, right? So the components are given, right? Okay, find and draw. I think we need to draw the graph also, and we need to find potentials, right? Assume v equal to 0, v at x is equal to 0. So let us take that potential is 0, and to some point we need to calculate potential. So can we draw the potential graph? Can we find the equation of potential? So let us first find equation of potential. So here, first of all, this point, if you see here, this point here, origin. So origin, they have given potential is 0. At any point here, potential you want to calculate. So change of potential delta V, directly we can write as integration of minus E dx, right? Ex dx, because along the x component. Now one thing is sure, that this area we have to calculate that integration. So this area we can calculate. So here to here distance is x. Let us say distance is x. And what is this height? What is this height? This height we can calculate, because we need the slope of the graph. So do we have the slope or not? From the graph, try to find out what is the slope of this graph. So I think we can definitely find out. So if you see 1,000 is happening at 1, or 2,000 is happening as 2. So this slope, or tan theta, we have this value as 1,000 by 1, or that means 1,000. That means you know the slope of this graph, right? So this height we can calculate. This height will be what? Because let us say that this is y. So y by x is tan theta. So y is equal to x tan theta. Y is equal to x tan theta, and tan theta is 1,000. So that is 1,000x. Now let us calculate area. So change of potential, V minus initial potential is 0. Change of potential minus, this is area. Area under graph is what? Half into base. Base is x, and height is what? 1,000x. So from here you got the potential is equal to, this is minus of course, and this is 500x square. So this potential, you can see this is the equation of potential. And now you can plot this function. If you want, you can plot this function. What is big deal about it? Nothing, right? So you can plot this v versus x graph. V versus x graph, plot it. This time, what type of function it is? It is like y equal to minus x square. Y equal to minus x square. Or you can say x square is equal to, like x square equal to minus 4ax form. It's a parabola, right? X square is equal to 4ax is what form? X is equal to 4x is like this form upward. Now this is like downward form. So you can draw that graph. It is not a big thing. But also note here one important thing, that it is a symmetric graph. Either if you put x as positive or x as negative, y will be always negative. So y graph is going to be like this. parabola like this. This is a parabola, we can draw that, that's all, right? Let us move to the next question. Question number 3. What is the electric potential at point P? So there is a point here mentioned. At that point P, you have to calculate electric potential. And what else is given? Right? Some charged particles are kept at the corners, right? The distance d is 1.3 meter. Distance is also given, right? And the charges values are also given. So this point is in the same plane. So the only thing is that we need to know the distances. So what are these distances? Can we calculate these distances? This distance all will be same, right? That's the half of this diagonal. So we already know that this distance is going to be d by root 2, right? D by root 2, correct? Because total is how much? Root 2d, half of that d by root 2. So we know that. Now let us calculate potential at that. So all these charges we need to consider potential. So k q1 by distance. So k by d by root 2 we will take out. So basically you have to add the charges q1 plus q2 plus q3 plus q4. Just add them and quickly solve it, right? So such a simple question. If you want, now you can substitute value. K is 9 into 10 to the power 9, and this distance d, they have given the value. How much the distance is? 1.3 meter. 1.3 root 2 will go in the numerator. Root 2 goes in the numerator. And what is the sum of these charges? All are nanocoulomb. Just add them. Okay, so you can see that how much this will become. Add 12 plus 31. How much it is? It becomes 43, correct? It becomes 43. 43. 43 plus 17 you add. 43 plus 17. 60, correct? 60. Now 60 minus 24 you do. 60 minus 24. How much? 60 minus 24, 36, right? 36 you will be getting. So 36 nanocoulomb 10 to the power minus 9. Over, now you can do very easy calculation. 10 to the power will go away anyway, right? And this is 9 into, so you got the answer. I think this calculation you can do. So 9 into 36, right? 9 times 36, 9 times 36 into root 2 by 1.3. This I am leaving the calculation up to you. You can definitely do this calculation. This unit is in volts. Okay, let us move to the next question. Question number 4. In this figure, 12 electrons of charge are equally spaced. So there is, some kind of a ring is given and some number of 12 charges are there which are kept equally spaced here, right? And fixed around a circle like this. It is given equally spaced relative to v equal to 0, v 0 at infinity, which is the normal assumption, right? What are the electric potential and electric field at the center C of the circle due to each of these electrons? So they are asking that what is the electric field and potential. Two things they are asking, field and potential. And note that here when you are calculating the potential and when you are calculating the field, note that field is a vector quantity. Electric field is a vector quantity, so you have to do vector addition. But when you are calculating the potential, that is not a vector, that's a scalar which you can simply add them, right? Only thing is required is charge and distance. So note that when you want to calculate potential here, because all the charges are equidistant. So for in the first case, if you calculate potential in the case of circle where it is equally spaced, or even if it is unequally spaced, it is not going to matter. Note that even if it is unequally spaced, this spacing is not matter. What is matter is this distance. These distance is only matter. All the same charges are there and distances are same. So you need to simply consider the addition of that k by r distance, that radius, and q1 q2. So simply you can add these all the charges. You can add from first to You can add this qi from I going from 1 to 12, I going to 1 to 12, all these 12 charges you can simply add in the calculate. So this answer is going to be same in both the cases. It doesn't matter whether the charges are separated equally or unequally, right? But what about the field calculation, electric field calculation? In this, note that electric field is going to be zero because of symmetric distribution. Because of symmetric distribution, field is going to be zero here in that first case, right? Here in this case, electric field is going to be zero. Net field will be zero. Now, what about in this case? Will the field will be zero? Is the field going to be zero or not, right? So is there any symmetricity above and below, or is it completely unsymmetric? If it is completely unsymmetric, then we need to calculate at what angles these are, field created due to each charges, and then we try to do that calculation. But here I think we cannot, in values of angles are not given, so we can just leave it. The idea that here field will not be zero, so some field will exist here. Net field is not going to be zero, some direction will be there, right? That's what it means. Now let us move to the next question, right? Let us go to the next question on 5. Figure shows a thin plastic rod of length. So there is a plastic rod means insulator, you can consider some length is given, right? And positive charge distribution is there uniformly, and potential is 0 at infinity. Find the electric potential at point P1 on the axis. So some point there, right, along the rod, that is the point. Now that distance is also given. How do we calculate that? Do we have any result? Do we have any formula? We can derive a very simple formula. Let us try to derive it. Suppose that this is the rod, like this case here. Some charges are distributed, right? Some charges are distributed q, and the length is l, and you want to find potential here which is along this point, right? So let us consider this point and let us calculate that. Okay, let us try to calculate the potential at this point. So first of all, you have to choose element, and this distance they have given d, and this distance will be l plus d. So we are going to choose a small element of thickness dx at a position of x, and this x will vary from d to l plus d, right? Now let us first of all calculate potential due to this small point charge. So that potential here V dV can be written as k dq by x, and this dq can be written as lambda means charge per unit length, charge by length, lambda into the length dx, right? Lambda dx divided by x is also there. Now we are going to integrate this, so let us integrate this. So when you are going to integrate it, right, from one point to another point, what we want to calculate first of all, so you can integrate it. So basically you will be calculating potential difference, right? You will be calculating potential difference. So let us calculate right hand side. What do we get it from here? So we are going to get kq by l, it will become ln x, right? And let us say that if you are not sure of that, then you can, give some value plus some constant you have to do if you are not sure of integration, right? If you are not sure of the limits of integration, right? But here we are sure that we are going from this point x is equal to d to x is equal to l plus d. By the way, what they are asking in the question? Okay, find the electric potential at point P1 on the axis at a distance d is equal to this of the rod. Okay, they are asking at a particular point. So we can write the potential difference if you take the limit. Let us not take the limit right now. I have just integrated v. So v comes out as kq by l ln x plus some constant of integration I can do, right? And note that if I put x is equal to infinity here, this v has to be 0. V has to be 0. So we will be able to calculate what is the constant of integration. Constant of integration. Otherwise, we can take the potential difference. Let us calculate potential difference. If you take potential difference, then limit you can now substitute. When you substitute the limit, what is the limit going from d to L plus d? So d to L plus d means what? Upper limit is L plus d. So L plus d by d. This is the calculation. Now you need to substitute the values and you can calculate this, right? You can substitute the values and you can calculate this. So the concept of potential at infinity we can calculate, and this what we are calculating is not the potential difference. This is the potential difference, right? And so we can say that this is the ln x in terms of that is the potential, because potential at infinity is taken as 0, right? So let us just consider this equation, which is the potential difference is same as the potential only. We can take it like this, but note that if x is 0 we cannot define it, that so this function may not be defined at some places. Okay, so you can just substitute. So they definitely they are asking potential difference, so we can calculate this, right? And if we can calculate it, what will be that? What will be these values? We can substitute that. Also note that there may be confusion here, like this side potential difference are we calculating, and this side we are taking the x variation. So what are we doing actually here? What are we doing? We are calculating potential at this point. So this represents the potential at that point only. This represents the potential at that point, not difference. You can say that this is potential at that point. Okay, this is the potential. This is the potential. So you can take the limit this side as potential from infinity to this. Now this is the important thing to note first of all. So this integration which we are doing is the potential difference. You can write potential difference, but you may think of which potential difference it is. So you are calculating here potential contribution due to each element you are calculating, and this side you are taking from distance. You are going from infinity to this. Yes, I think this is potential from infinity to the potential at p. So this will be potential only at that point. Okay, this is a major confusion here, no? Because here right hand side x we are varying, and here you are writing potential difference left side. So what is that left side potential difference? Is it the potential difference from left side to right side on the rod, or is it the potential difference of the from infinity to that point? So this potential difference as per the definition is from infinity to that point. It is the work done in moving a charge from infinity to that point. So that is the potential which you are calculating, and potential at infinity is 0. So this difference v minus v infinity is going to be v. So this is the exact formula for potential at that point. Yes, this is a very good point. Otherwise this will be a confusion in many derivation due to continuous charge distribution, right? Now you can substitute values and you can do the calculations. Let us move next. Question number 6. A plastic disc of radius r. So there is a disc here. We can see here there is a disc and some radius is given here. Charged on one side with a uniform surface density, and then three quadrants of the disc are removed. The remaining quadrant is shown in the figure with potential again same way infinity 0. What is the potential due to remaining quadrant at a point P which is on the central axis of the original disk? How do we calculate it? Here in this question you have removed 3/4, so only 1/4 are remaining quadrant. So let me redraw this diagram. So the idea is that on this axis of the disk we have to calculate, and we have full disk, but we have removed some portion of the disk and we have only now 1/4 remaining. 1/4, this angle is 90 degree. This much charge is only remaining. Okay, how do you calculate this potential? So we can do the calculation exactly in the same manner, but only thing is that the full disk contribution is not there. The contribution is now only one fourth of the disk. So you know the formula for potential on the axis, right? Full potential to full disk. Now this is one fourth of simple calculation. One fourth you have to take. That's all, because charges have got divided by one fourth, right? And the equal quadrant will have same potential and say scalar quantities. That is why it is not getting affected, right? So we can take potential. Okay, tell me formula for potential on the axis of a disk. Remember that? Sigma by 2 epsilon naught, right? Root under x square plus r square minus x. Correct? That's the formula, right? So we are getting this formula we already know. X is the distance of this point from the center of the disk. So these values are given, right? All these values are given here. X is that D, capital D. So now what we need to do? So sigma, which was the here, what is this sigma? Sigma is charge per unit area. Sigma is charge per unit area. So what is the area now? Because see, so sigma is getting divided. Sigma is getting divided because sigma was charged by area, but now you have divided the area as like one fourth. So sigma is going to be one fourth of that, right? So here you can just put a factor of 4 in the denominator, right? So just put 1 by 4. Okay, that is what is the potential, where sigma is the charge over the total area. Remember, this sigma here is the total charge by total area, which is pi r square, because total charge was spread over that area, right? Or anyway, they have directly given here the charge density, right? Charge density, then these quadrants of the disk are removed, right? So this charge q was divided over. Now there is a question here that in this charge is not appearing in this, right? This formula is due to the full disk, and now we can just take as 1 by 4th. But suppose if I don't put 1 by 4th, it looks like, because sigma is constant, this should remain as constant, but that is not the case, because you are removing some, charges. So because you are removing some part of the charges, definitely the potential contribution is going to change, right? So one fourth you have to do, and sigma and other values are given here totally, then we can calculate that, right? Because total charge was distributed over total area. Total charge was distributed over total area. Now what is happening? Charge is distributed only some portion of that. So this formula was for full, and we are taking 1 by 4. There can be confusion here. So we'll make this confusion clear. One fourth will take. If it is half, then we should take as half, right? We should take as half. You may say that sigma is not changing, but sigma is not changing, but the total amount of charge is changing, right? So total amount of charge was total, equally it was spread. Now here the charge has become one fourth of that, right? One fourth of that, correct? Charge, total charge q was, let us say, spread or charge density. So here this was like sigma was charged by area. Now you may say that area has become one fourth. There can be confusion. Note that there can be confusion. That's why we are discussing. Suppose they say that the same charge q has been given to this place on this one fourth, then charge density would change. But here charge density is not changing. Note that charge density is not changing, but total charge will be changing, right? Okay, let us move to the next. Find the potential due to an infinite sheet of charge at a distance x from it. Assume that the potential 0 at a distance c from it. Infinite sheet we have. So we know the formula for field here. So it's a infinite sheet, in all direction it is going. So let us consider that some distance r from it. We know the field. Let us say that it is positive distribution of charges. Charges are positive. So here field will be what? Field formula is sigma by 2 epsilon naught. We know it's a uniform field, right? What we want to calculate? They have given the potential is 0 at a distance a from it. So suppose some distance from here, at some distance which is a distance, so that means r is equal to a. Here potential is 0 and you want to find potential where you want to find potential at a distance x in general. So r is equal to x, let us say. Here moving at a distance r equal to x. Here you want to find potential. So what you will do? Here directly you will apply delta v is equal to minus E dot delta r. Why we should apply like this? Because field is uniform. So let us apply delta v. So you are going from this point to that point. So change of potential v minus 0 and minus field value. Field is what? Sigma by 2 epsilon naught. And you are moving in the direction of field. So cos 0 degree 1. And change of positions, which will be x minus a, x minus a, x minus a. So this is what is v. Potential at that point will be this only, minus will be there. If you want minus, take inside. So sigma by 2 epsilon naught a minus x. This is the potential at that point, right? Let us move to the next. Consider two concentric cells shown in the figure. There are two concentric cells are given. Okay, one of them is charge q. Here, if it is not visible, I will draw it again. Let me draw this again. So this is one inner cell and this is one outer cell. Okay, right. Now what is the question here? Question says that, what is the question saying? That charge q, one of them has charge q, the inner has charge q, right? Radius r, and other outer cell minus q. Okay, ready. Find the potential at the surface of the outer cell. Let me redraw this. So here charge is q given and here charge is minus q given, right? This radius is capital R, this radius is 2 times of r. Potential at the surface of the outer cell and at the center. So we need to calculate potential at the center and potential at this. Let us write this as first cell. Let us write this as 0, 1 and 2. Right? 0 is the center, 1 is the first surface, 2 is the second surface. You have to calculate potential at 0 and potential at 2. Right? How do we do that? So first of all, there will be charges distributions can happen, although distribution of charges can happen due to induction. But let us try to calculate potential at 0. So potential at the center will be due to the first charge distribution, which means due to the first sphere and due to second sphere. So potential at O due to 1 plus potential at O due to 2. Let us try to simply write it. So this point is inside the sphere 1 and this point is also inside the sphere 2. So for points inside, the formula for potential, right? Potential is constant. So kq by r, simply you can write k. What is the charge here? Charge is q, kq by r. R radius is capital R, right? Similarly, potential due to the outer surface is k minus q divided by 2r. This radius is 2r. That's all. Let us solve this. So this is the potential at center. How much this will be coming? Half only will come. So k q by 2r. This is the answer. Now what about potential at point 2? Potential at point 2. So potential at point 2, when you are calculating, so potential at 2 will be due to its own charge and due to the first sphere. So potential due to 2 will be potential on 2 due to charge 1 plus potential of 2 due to its own charge. Let us try to calculate how much this will come. So potential 2 due to this. So this is a spherical cell on the surface of a spherical cell, that is also k cube by r only. So on 2 due to this will be k cube by r, and due to 1 what it will be, due to 1 outside point, because point 2 is outside of sphere 1. So k cube by this radius, which is 2r, right, plus k this charge minus q, and by radius 2r. So this is going to cancel out, and potential at point 2 is going to be 0. Right, this is how we are going to use the results of potential due to spherical cells. For inside formula, everywhere constant, on the surface also constant, outside only changes, right? Then let us move to the next. Similarly, there is a thin conducting spherical cell of radius r, radius and all these things are given, charge is given, right? What are the electric potential and magnitude of the electric field on surface, on the surface, and at B r is equal to 2 r and r equal to 0.5 r. On the surface means r equal to capital R. At this surface you can say, and next is at r equal to, second case is r equal to 2r, r equal to 2r, and third case is r is equal to 0.5 r, or you can say r by 2, r by 2, right? So let us consider this cell. So this is the cell here, it has some charge already. So some charge or some thickness they have shown, but it is like a negligible thickness. Okay, so how to solve it? Charge is there, radius is there, we want to calculate at this surface. So you know direct formula, potential at this surface. First case I am writing, potential at this surface is k q whatever charge and that radius. Simply substitute the values, you can calculate. Let us move to the second case. Second case, potential at 2r, 2r means outside point. So k q by 2r, right? This you can calculate. What is the third case? Inside point and up to the surface, that remains the same, right? So this will be same as k q by r. So the answer for first part and third part is same. Second part is going to be half of that, right? So you will be able to solve this question. Let us move next. Question number 10. Assume that a point charge q is projected from a large distance toward the center of a fixed charge ring along the axis. What should be its initial velocity so that the charge may reach the other side of infinity? Let's understand this question. A point charge is projected from large distance toward the center of fixed charge ring. Suppose this is a charge ring and this charge ring is fixed, it is not moving. Okay, this charge will have some charge distribution will be there, and from the very large distance along its axis, very large distance, a charged particle is projected. This distance is very large means you can consider this distance is infinity right now, and you are projecting with some speed. What should be initial speed? Let us say this speed is u, right, and its radius is r. This radius is r, some charge is there. Okay, small q, capital Q, whatever you want it. What should be initial velocity so that charge may reach the other side of infinity? Other side of infinity means that side infinity. Here it should be able to reach. So that means you must throw it with some speed, and note that as it is going to come here, it is under repulsion, so it is under retardation. So its speed will be decreasing, and somehow or the other, if it is able to reach here a little bit near to the center, then definitely it may cross that and it may go that side. So minimum condition of speed will be, minimum speed here should be such that it is just able to reach here. So here speed should be 0. Now you can apply energy conservation, right? So when it was infinite distance, note that the potential energy of this initially, electrostatic potential energy was 0 initially, right? But it has kinetic energy. When it comes here, kinetic energy is 0. but it has final potential energy. So we know the potential energies here. What is the potential energy here? K, this charge is a small charge, right? So Kqqq by the distance r, right? That's the potential energy. Now let us balance energies. That's all. Just balance energy. So here energy only is kinetic, half mq square. And finally here only potential energy is there. So kqqq by r. That's all. Over you can calculate speed. So u will be root under 2k capital Q small q by m into r. Okay, if you want, you can substitute values. This is what you will get. Okay, let us move to the next. Question number 11. Figure shows three pairs of parallel plates with the same separation in the electric potential of each plate. The electric field between the plate is uniform and perpendicular to the plate. Rank the pairs according to the magnitude of the field between plates and greatest first. For which pair is the field pointing rightward? If an electron is released midway between the third pair of plates, does it remain there? Move right or constant speed? Move left, constant speed, accelerate or. Let us first see the figure. Okay, you can see here. So potentials are they are given. They are asking electric field. So let us try to calculate electric field between them. Direct formula we have. They have also note that potentials are different here. Potentials are different. They have different potential. So how do we calculate the electric field in between? But one thing is sure that this is a higher potential, lower potential. So field lines will be coming like this way. Electric field lines will be coming like this way. Correct? Electric field lines will be coming like this way. Here this is higher, this is lower. So electric field lines again same way. But what about the values of electric field? Electric field values also will not be same. Here both are minus. Because both are minus, we have to take the higher potential. Higher will be minus 200, lower will be minus 400, right? Because minus if you go more, it will become lower. Minus if you go less, it will become more higher, right? So here the field lines must go like this. This is how field lines should go. This is field line. So can we calculate the field line, and the distances will be given between the plate. Let us say the distances are given everywhere d. So what is the potential difference? The formula for potential difference, V is equal to minus E into dr. So suppose you are going from here to here. Let us say you are going from here to here, or you may go opposite. Let us move in the direction of field. Okay, so when you go E into delta r only, because field is constant, so E into delta r. Let us write delta r. So potential difference when you go from higher to lower, how much will be the change of potential? It will become minus, right? Minus 50 minus 150, so this become minus 200 and minus C, and this distance which is d here. So basically in the first case you are calculating this field is 200 by d. 200 by d. In the same manner, let us just write that. Let us just write the magnitudes of electric field here also. So potential difference by distance. So potential difference is how much? 200 minus 20 difference you take, so that becomes how much? 220. 220. So 220 by d. Okay, d will be the distance. Similarly here, what is the electric field? Uniform field. Difference is also 200 here also. 200 by d. So you got the field in all the three cases, and we can clearly see that this field is stronger. This field is higher in magnitude, and those first and last case field values are same. Only thing, directions are opposite. Directions are opposite, right? So what is that other part of the question is that if you keep a electron here, that's what they are asking. If an electron is released midway between third pair of plate, does it remain there? Move right, move left, accelerate. What will happen? So if you keep a electron here, electron is a negative charge. It goes opposite of field line. So it will be going in this direction. Opposite means it will move towards left side because field is towards right side, and it will not just move, it will accelerate because there is electric field, right? That's the answer. Let us move next. Question number 12. Which potential graph describes the electric field shown here? Which potential graph describes the electric field shown here? Here there is a graph of electric field. So here you can see that electric field is like parallel field lines. You can clearly see here. If it is not visible, I will redraw that. So here the field lines are like this way, parallel field lines, like this, like this, like this. Field lines are parallel. Now field lines are parallel. We need to choose the potential graph. How does the potential graph will look like? What do you think how the potential graph will look like? Potential graph. Yes. Field is only along the y-axis and it's a constant field. Note that the field is constant. Field is a uniform field. And in which direction field is existing? Field is existing along the y direction. There is no field along x-axis. There is no field along x-axis. So you will see that in all these graph, the variation of potential is happening only along y-axis. If they draw the graph of v versus x graph, there is no, that will be 0. Why? Because along x-axis there is no field. Field is 0. Along y-axis field is there. So you have to study only the, this is like y component of field, which is E. So what you will write the equation? Yes. What is the equation you are going to write? You will write that delta V is equal to minus E into delta R. But you are going along y-axis, so this change of potential will be along the y-axis. Along the y-axis, and along the y-axis, change of potential will be what? Minus E into delta R is like y here. Let us say that you have started from origin. So this is like y or delta y also. If you can write, you can write that. Okay. So this is like delta y. You can write it like delta y. No problem. So delta V is equal to minus E into delta Y we will write. Okay, so delta V. So definitely here delta V by delta E, delta V by delta Y graph is like minus E. Correct? So this slope of this graph is going to be a constant with a negative. So negative slope must be there. So this is not possible. This is not correct. Okay, this is not going to be correct. A is not going to be correct. Here it is showing constant potential. That is also not correct. Field is constant, but potential will be a linear function. Potential is depending linearly on y. So it is a straight line definitely with negative slope. You can choose this. Others you can reject. Clear? So we got the idea. Let us move next. Question number 13. Is the electrostatic field pattern shown in the figure possible? Now question is that is it possible or not? Field is possible or not? This kind of pattern of field is possible or not? Let us try to understand this. Here what we can see that this some of the field lines are here closer they have drawn, and then here field lines are farther. Field lines are farther. So here field lines are closer, here field lines are farther. Is it possible or not? Generally, when you think now the field lines are parallel means uniform field. Here also field lines are parallel. So does that means it is uniform? So wherever field lines are very closer, their field strength is more. Wherever field lines are farther, their field strength is less. So definitely field lines is not, of course lines are parallel, but the field is not uniform. Uniform field means parallel lines with equal distances. Right here distances are not equal. So question is what? Is it possible or not? Is it possible or not? So let us try to think of some way, try to think about it. Suppose if I try to make a Gaussian surface like this, I make a rectangular Gaussian surface. If I made like this type of Gaussian surface, what will happen? What will happen? Of course, flux will be zero, whatever the field lines. But let us say try to move a charged particle in this. Let us take small charged particle and let us say you move along this path, along this rectangular path, like this. How do we know whether it is possible or not? So one thing, one idea is that of course flux will not work because flux may get cancelled out. What you can think about is properties of field lines. Of course field lines are not cutting, so this is possible. Then other properties you can apply, but one important property is conservative. So if it is conservative, then yes, it is possible. Non-conservative means it cannot be field lines, at least not due to electric charges. So if you are thinking that this is due to electric charges or charge distribution, then it must be conservative. Can we think of doing like conservative property? So if you move a charge in the loop, the total work done must be zero. Work done must be zero. Let us try this. Now here note that the field is different. Here let us say that field is E1 and here field is E2. So note that when you are going from here to here and here to here, they will cancel out because here you are going the same higher field and while going this way, and same higher field while going this way, because anyway here the motion of charged particle is perpendicular because you are moving perpendicular to field, right? This angle is 90 degrees. So you are moving perpendicular to force. So that force, electric force, will not do work while moving perpendicular, but while moving parallelly definitely it will do. Now let us say you are moving from here to here, here to here. So this field, assume that it's positive charge, so it will do some work. So let us say that this is point 1, point 2, point 3, point 4. So while going from 1 to 2, there is a work done. What is that? And let us say that this distance is xx and this is yy. Okay, so here work done will be force into distance, so e2, right, charge into field multiplied by distance, right? Then work done in 2 to 3, 2 to 3 there is no work done because you are moving perpendicular. Similarly work done 3 to 4, 3 to 4 you calculate, you are going opposite, so work will be negative, right, negative. So charge into field e1 and distance is same x. Now you are going from 4 to 1, again you are moving perpendicular, work will be 0. So let us calculate the total work in the loop. So work in this loop must be sum of all this. When you do sum of all this, you can see that you will get qx e2 minus e1. Now because the field e1 e2 are not equal, this is not going to be 0. That means work done in a loop is not going to be 0. That means it is non-conservative, which is not possible. That means this field is not possible because work done in a closed loop is not going to be 0. Okay, very important concept. Okay, let us move to the next question. Number 14. A dipole moment is placed at origin along x-axis. Another dipole moment is kept at some point along y-axis. Find the resultant potential at, okay. So at the origin, one dipole moment is kept like this, and another on the y-axis just above this, because this is x-axis and this is y-axis, right? So this is one dipole moment. Another dipole moment is kept along y-axis like this way, right? So these are having same dipole moment, pp, p and p. Okay, both are pp. But here one of them is at the origin, this and this, so their centers are given, right? Origin and this value, this is at 1 0 1 0, and this is of course 0 0 0. Okay, now question is find resultant potential at 1 comma 0 comma 0, this point 1 comma 0 comma 0. We need to calculate potential here. How do we calculate potential? So definitely this point for this dipole, this is the what? What about this? This is the axial point. So axial point potential we can calculate. We know the formula, but equatorial point potential is 0, right? So we can directly use potential at the axial point. Calculate potential at the axial point. What is that? K P Kp by what? What is the formula for potential due to a dipole? Do we know that formula for potential? Suppose this is charges, right? This is negative charge, this is negative charge, minus q, this is positive charge. So we have to remember that formula, the distance at this distance. So this distance, if you take at the center, this distance becomes r minus a, and this distance become r plus a, right? So potential due to both the charges, so k q by r plus a plus k minus q by r minus a. Sorry, this will become r minus kq by kq by r minus a, kq by r plus a. So do this calculation. So kq comes out. This become r square minus a square. So is it a short dipole or not? That also we need to look at it. Is it given short dipole? They have not mentioned anything. So let us know this formula. So r square minus a square, kq we have taken common. So r plus a minus of r. So this will become 2a. That becomes kp by r square minus a square. This formula better to remember that. Okay, so kp, this is the formula for potential, uh, but they have not mentioned what is a another thing. You can treat it as short dipole. Short dipole means a you are going to neglect in the denominator. So kp by r square, kp by r square. R here is what? R is 1 here, correct? R is 1 here. So this will become just kp. Okay. Due to this, what about due to that? Due to this also we need to think about it. So for that you need to see what is the angle made by this angle. This angle in this direction is important. Angle with this, right? This angle is how much? So note that this is 1 1, so this is 45 degree, 45 degrees. So this angle is 135 degree, 135 degrees. So potential due to that angle, you know, you have a formula for that. So that formula also you need to add that one plus due to this potential. So k p dot r cap you have to do, or p dot r vector you have to do. Let us do that. So dot product means what? Kp cos theta. So k this p this, and this vector, what is the magnitude of this? What is the magnitude of this? This is root 2, right? So root 2 cos theta, cos of 135 degree. Cos of 135 degree is what? Cos of 135 we should know. We can write cos as, of course it will be negative, cos 90 plus sin it. So minus 1 by root 2. Minus 1 by root 2 it will come, right? Right. Then r cube. R cube means this r is root 2, root 2 cube. So root 2 cube means 2 root 2. So now what do you get from here? We need to add this, right? So net potential at that point, net potential will be how much? This is kp due to this, and that will come as minus. Here root 2 got cancelled. So kp by 2 root 2 is going to come, right? 2 root 2. That's what it is. You can rearrange this kp 1 minus 1 by 2 root 2. This will be the answer. Clear? Yes. Resultant potential and field also we have to calculate. Field calculation again same way, but field is a vector quantity. Vector addition you have to do, right? So how will you do vector addition? Let me try for field. So field calculation, if we do this potential and this dipole moment will create a field here. That is axial field. What is that field? That field I will write directly 2 times Kp, 2 times Kp, right? By what? R cube, short dipole, R cube. R cube means 1 cube here. This is also 2 Kp. What about this one? This one, due to this, now this was in this direction, and due to this point, how do you do that? So I think you need to resolve this. So this angle is 45 degree here. So P you need to resolve it. Resolve P in this direction, P by root 2, and also in this direction, P by root 2. Okay, note that for this P by root 2, for this P by root 2, for this P by root 2, we will have a field in the same direction, axial field. Again 2 kp by r cube. R means this distance. This distance is root 2, right? Root 2 cube. And also note that this p is p by root 2. We need to make sure we write properly component. 2 kp root 2 axial by r cube. R cube is root 2. So 2 root 2 will come from here. So this 2 got cancelled. This comes as kp by 2, right? In this direction we are getting. Then what about this? Due to this direction, equatorial field will be coming in this manner. Equatorial field will be coming perpendicular to that. How much will be that? K p, that component p by r cube. R cube is again 2 root 2. So this is how much? This is kp by 4. Okay. So we have now three things to add here. What are this? What they are vector? Okay. So one is 2 kp, another is along this line, one is along this line, which will be kp by 2, and one is perpendicular to this line, which is kp by 4. Now how can you do this addition? It is easy to do that. Vector addition we have to do, right? These three fields. How do you do vector addition? You can do resolution. Best way is to do the resolution. So let us do resolution in x and y component. Okay, x and y component, let us resolve that. So this kp by 2 and this angle is 45 degree, right? 45 degree. So kp by root 2 component in this direction will be by root 2. So kp by root 2 will come due to this. Similarly, this side also kp by 2 root 2, kp by 2 root 2 will come. Now similarly, what about this kp by 4? Kp by 4 also you need to resolve in the same manner, this component and this component. So kp by 4 root 2, this also kp by 4 root 2 over. Now let us add all the component along x-axis. So x-axis component is 2 kp, and this is kp by 4 root 2, kp by 2 root 2. So how much it will be? This is 2 kp. I will subtract that, right? So if I take LCM as 4 root 2, 4 root 2, so 2 and 3, 3 times kp by 4 root 2. What about the vertical component? Vertical component is this side. So kp by 2 root 2 minus kp by 4 root 2. So that will give us kp by 4 root 2, right? Now how much is this x component? Solve it. So if you take LCM 4 root 2, what it will be? You can solve it. So 4 into 2, 8 root 2 minus 8 root 2 minus 3, 8 root 2 minus 3 kp, correct? Now resultant field which you want to calculate will be root under this square plus this square. I think you can do that. So kp by 4 root 2 whole square plus 8 root 2 minus 3 by 4 root 2 times kp. So kp, then square of that. So I think kp you can take out square of this, and kp square also will be there. So kp will come out. You can solve, you can simplify this. This is like the resultant or net field. Little bit complex calculation. Okay, fine. Let us move to the next. Question number 15. Three charges Q, Q minus 2Q are located at the vertex equilateral triangle. Find the dipole moment of the combination. So let me write what are the charges. Okay, here charges is minus 2Q, here charges is Q, here charges also Q. Let us quickly make it, because this minus 2Q, you can write this as minus Q minus Q. So this will form one dipole and this will form another dipole. Distances are same, AA. So this dipole will be going in which direction? It will be going in this direction. This will also be going in this direction. Right angle is 60 degree between them. So we can just add these two p factor at an angle of 60 degree. Resultant will be coming downward, right? So root 3 times p, correct? So this will be the net dipole moment, and this p is nothing but q into a. And if you want to write this net as a vector, if you want to write this as a net as a vector, so minus root 3 q a j cap. Minus j cap means downward it is coming, exactly, that's the answer. Let us move next. Question number 16. Figure, again there are some charge distribution here, right? Fixed positions. What is the electric potential energy U of the system of charges? I assume that distances are given. This is again, now three charges are there. Here this is Q2, here this is Q1, Q2, Q3, right? Let us take that Q1, Q2, Q3, and distances are D, D, D. So potential energy of this system will be, system potential energy means potential energy between first and second, potential energy becomes second and third, plus potential energy between third and one, like this. Three pair will come, pair you make, three pairs will come. Now potential energy formula is K, Q1, Q2, right? So K by distance you take out, and this will become Q1, Q2 plus Q2, Q3 plus Q3, Q1, right? And just multiply and do the calculation. That will be the total potential energy of the system. Let us move next. Question number 17. Find the potential at point A due to charge Q. Charge Q. Okay. Charge on the outer surface of this cell and total potential. So I will redraw this diagram because it may not look clear. So what is that? There is a cell. Okay, there is a cell. Find the potential at point A due to. So there are charges are there. One charge is outside here, capital. So this is the center O, let us say, and this is point A. Here, this is point A. Okay, this point is point A, which is at a distance of r by 2, and this point outside point is at a distance of 2r. R is the radius of this cell. Now question is that a point A due to charge Q and charge on the outer surface of the conducting cell. So what are the charges they have mentioned? Here charge is given here. Here definitely this charge is like a point charge. And this outer sphere is also there. Find the potential at point A due to charge Q. And second case, okay, so there are parts of the question. First part let us solve. We have to calculate potential at this point due to that charge alone. So due to that charge alone, when you are calculating, so due to that charge only, so that distance you need to consider. So what will be that potential at A due to that charge? So that will be just K Q by distance 2r. Okay, now second part they are saying that potential at A due to charge on the, let us say the charge on the outer sphere is also Q. Now due to this charge, what will be potential? So potential now due to this cell will be K Q by radius of this cell. This distance is not important because potential remain constant throughout, which is same as potential at the surface. So that radius is R, you have to use. Okay. Then potential at A. Total potential means you need to add them. So net potential, now you add from these two. You have to add these two. Let us just add these two potential. So it will become k cube by 2r plus k cube by this. Add this, it will become what? K cube 3 by 2. 3 by 2 k cube by r. Right? That will be the answer. Let us move to the next. Question number 18. Question number 18. Find the potential of the cells in the situation shown. There are 3 cells are given, right? Then what we need to do? The charge distribution on each of the cells after the inner and outer cells and connected by connecting wire. First, let us do the calculation first part. Potential of the cells in the situation shown in figure. What is the situation in the figure? Let me draw this. So there are 3 cells. 1, 2, 3. And what are the charges? Charges on the inner is q, second is 2q, and third is 3q. And radiuses are given as r, 2r, 3r. Right? Where we want to calculate potential? Potential of the cells in this situation. Cells, that means what is the potential of first? Let us note that this is the first cell and this is second, this is third. So how to calculate potential of one? We discussed that. To calculate potential of one, so potential at this will be created due to its own charge plus potential at 1 will be created due to second plus potential at 1 will be created due to third. Now let us solve this. Let us calculate this, right? So on 1 due to itself will be k q by r plus on 1 due to 2, so it's an inner point, so k, what is charge, 2q divided by that radius which is 2r plus due to the third one, again this is inner point, so k 3q by radius 3r, right? So 2 will get cancelled, 3 will get cancelled, so this will come 3 k cube by r. That will be the answer, first part. Now they are saying that the charge distribution on each of the cells after the inner cell and the outer cells are connected by a conducting wire. They are asking charge distribution when you connect them. When you connect them. So let us try this. Let us try. So this sphere, this sphere and this outermost sphere. Initially when it was not connected, what was the charges? And they are saying which one is connected? Which one is connected? Inner and outermost. That means first and third is connected. First and third is connected. So suppose if I connect, this is the first one, this is second one, this is third one. Second one is not connected, and note that here charge was q, 2q. Here it was q, 2q, 3q before connect. Now once you connect this inner one is connected here. I am showing the connection like this way. I am just showing the connection like this way, okay, because it is not intersecting here. So this is like a jump or kick happening. So these two are connected, inner and outermost. So what will happen when they are connected? What will happen when they are connected? One thing very important to note, their potential must become same, because if their potentials are not same, charges will flow. So when you connect them initially, charges will flow and finally they will get the same potential. That is the idea. Okay, same potential. How to find charge distributions? How to find charge distribution? So initially what was charge distribution? They are not asking, they are not bothered. Initially also if you want to show charge distribution, you can show. And note that induction happen from inside to outside, not from outside to inside. So suppose if I write this charge as q, so due to this here minus q will happen. Due to this minus q, now remaining charge here will be how much? Because total charge must be 2q. So here you must write 3q, because 3q minus q will give us 2q. Now here on the outer surface 3q, so here must be again minus 3q, and here total charges is 3q, so here must be plus 6q, right? So plus 6 minus 3 will give 3. So this is charge distribution before. But in the calculation of potential charge distribution is not important. Okay, right. But now what will be charge distribution? Right now you do not know what will be the charge. Let us say that after after connecting charges here on the outer surface is x. Try to go by the same approach, x. So induction will happen here, minus x will happen, minus x will happen. Then on the outer surface here total charge is 2q, so this will be then 2q minus x on this surface. Then here it must be 2q plus x, 2q plus x. Induction will happen or induction will not happen. What do you think about it? Induction will happen or induction will not happen. But let us consider induction because they are very close by. But it is also in contact. That is also there. So 2q plus x. Now remaining charge will be how much? Remaining was 3q, right? 3q was there. So this will be q minus x. Correct? Note that we need to take opposite of that. So opposite means minus 2q plus x we need to take opposite. So now here will be how much? Here will be how much? Total charge must be 3q. 3q. So it will be 5q. 5q minus, because minus x plus x will cancel. 5q minus 2q will become 3q. Will this happen or not happen? How do you think about it? If I am thinking in terms of induction, this we are writing it. But see, one thing is also note that the total charge of first and third will be how much? 3 plus 3q plus q, 4q should be there. 4q should be there. Total charge must be 4q, right? So if you are taking this and this one, charges are not getting balanced because q and 3q must be there. So should we show induction effect or not? But we are taking x charge here. If you are doing induction effect, so induction effect should we show between them or not? We can show because they are not connected. They are not connected. This is x, this is minus x. Remaining charge is 2q minus x. And if you take from here to here induction, they are also not connected. We can take induction effect between them. So 2q minus x, then minus 2q plus x, minus 2q plus x. But this we cannot write 5q minus x. Why? If you write 5q minus x, it will not be balanced. So because total charges is how much? Here charge is q and outer is 3q. So total must be 4q. 4q charge must be there in between first and this last. So if it is x here, now it is minus 2q plus x it has become. How much charge must be in the outer surface? Can you guess out it? So we can write this as 6q because 6q minus 2q will give 4q, and we should write this as minus x. Why? Because this total sum of this plus this must give 4q. It must give 4q, correct? But here sum is giving 4q, but there is also x. What should we do here now? Think about it. We should also cancel about this one. So we should also put minus 2x. We should put minus 2x. So 6q minus 2x. Now if I take this is how much here? 6q minus 2q become 4q. 4q. Plus x minus 2x become minus x. So this minus x plus this x will cancel out. Now total charge will be 4q. Now it is balanced. Correct. This is correct now. Charge distribution. This is what we have to think about it. And also make sure that charge in the front and front faces must have opposite polarity because of induction. Now we are done with charge distribution. But what is the value of x? How to calculate that? So to calculate the value of x, we can try to take the same potential of point 1 and potential of point surface 3 must be same because we have connected. Now let us write the potential of 1. And note that what is the total charge here. Total charge, let us write total charge on this because of this. So here how much is the total charge coming? So this is coming as 4q minus x. This is the total charge now in this third one. Here total charge is 2q only, no problem in this. And here total charge is x. Okay, right. Now let us write potential of point 1. Potential of point 1 will be due to its own plus potential of 1 due to 2 plus potential of 1 due to 3. Let us write potential of 1. So here charge is x. So k charge is x, kq by radius is r, plus potential of this due to the second charge. Here how much charge is? 2q charge is there. So k into 2q divided by this radius is 2r, plus what is the charge on this? 4q minus x. So k into 4q minus x divided by radius, which will be 3r. Okay, this is potential of 1. And what about potential of 3? Let us write potential of 3. So potential of 3 is due to 1, potential of 3 due to 2, plus potential of 3 due to 3. Let us try to write. So this point due to 1, this charge, so this is outside. So k q is x, kq by this radius, which is 3r, plus k due to second, it is outside again. So k charge is 2q, and distance, again distance is 3r only, plus k charge is how much? 4q minus x, 4q minus x by the distance 3r. Now we have to equate v1 equal to v3, and we have to solve x. Once you solve x, you can tell all this distribution of charges, right? So what are the things going to cancel? Anything will happen, cancel or not? Think about it. It's a good question, but now we can try to solve. v1, let us write that. So kx by r, right? Kx by r, I will write it once. Kx by r plus k into 2q, so 2kq by 2r. 2 can get cancelled, it will become kq by r only, right? It will become kq by r. Then what else? Here k4q minus x by 3r. This is equal to this. So what will be this? Kx by 3r. 3r, if you want, you can take LCM. 3r you take LCM. So kx plus 2kq plus 4kq minus kx. Right? Open this bracket. Check out some calculation you do now. So this plus kx minus kx get cancelled. Here also you take LCM, left side also take LCM. So this will be 3r, correct? 3r. So it will be 3 times multiply. It will become 3kx. It will become 3kq. It will become 4kq minus kx is equal to this side how much? 6kq by 3r. So 3r will get cancelled. Kq terms also cancel out. How much do you get? Check out this. We need to calculate x. So 3kx minus kx, we get 2kx, and here 4kq plus 3kq, 7kq, that is 6. So minus kq it will become, because right, that will go away. So what is going to be x now? X will be minus q by 2. Very very good question. This is the answer. X is equal to minus q by 2. So now you can substitute the values of here, because now this, what is the x here? So x value is minus q by 2. Here it will be minus x is plus q by 2. Like that you can calculate now the charge distribution on each sphere. Okay. So this is a good question, good example, right? Let us move to the next. Okay, question number 19. Assume that two spherical concentric conductors like this, okay, cells of radius small r and capital R kept as shown. The inner cell is given a charge capital Q and outer cell is earth. Find the charge supplied by earth and the potential of the inner cell. Let me redraw this circuit. So what is there? That the inner cell is there, outer cell is there, and this cell is inner cell is given a charge q and it is earthed. Earth means what? Note that earthing means the potential of that cell becomes zero, because earth is considered to be zero potential, although earth has some potential, but it is almost negligible. We take as zero potential. Okay, so that means this will become 0 volt once you calculate, connect it. This is called earthing. Okay, we have done earthing. So due to earthing, the potential becomes zero. Okay, and this is small r and this is capital R. So what is the question? They are saying that inner cell is given q, outer cell is earth. Find the charge supplied by earth and the potential of the inner cell. So first of all, let us note that when you have not connected to earth, there will be induction. Induction will always be there. So here it is plus q, this will be minus q. And on the outer surface, it will become plus q, because this was neutral. Initially, it was neutral. But once you connect it, what happens, that earth will supply some charges. Earth will supply some charges to neutralize the outer surface. So how much earth will supply? Earth will supply minus q charge, so that the outer surface will become neutral. Okay, should it become neutral or what? Let me think about it. Will it become neutral? Suppose you do not know. Okay, let us think about it. We do not know how much earth has supplied. Why it should become neutral outer surface? Not necessary. It is not that it has to be neutralized completely. But one thing is that we know that its potential will become zero. Potential will become zero. So let us say we do not know what charge it is. Let us write this as a small charge. Earth has supplied some charge. Let us write this as plus q, because we do not know whether it is plus or minus. So earth is supplying a plus small q charge, but the potential of this surface should become zero. Okay. Now let us write the potential of this. So this is inner one and outer one is 2. So we know now that potential of 2 must be 0. But potential of 2 is potential of 2 due to 1 and potential of 2 due to 2. Right. So this calculation now we can do, and we can find out this is small q. Right. So potential at 2 due to 1 due to inner charge. So that is simple k. This I will remove. So this will become k q by outer. Outer is capital R, right? Plus its own charge. So what is the total charge? This plus minus is not at all there, right? Only this charge which is supplied by earth. So that is k q by capital R. This is going to be 0. Oh, that's what it is coming as same, right? So we are getting q as minus. So our guess was correct only, that earth is supplying minus q to make outside surface neutral. Okay, so this q supplied by earth is minus capital q. That is the answer for that. Then what is the question? Potential of inner cell. Now they are also asking the potential of inner cell. So same way, calculate potential of inner cell 1. So that will be potential due to 1 itself plus potential due to 2. So potential due to 1 will be k capital q by r, plus potential due to outer surface will be, sorry, here is small r, right? This is a small r. So k capital q by small r plus k, that total charge is small q, by capital R, and this small q is minus q. So this kq you can take common, it will become 1 by r minus 1 by capital R. Very good question, right? So that is the answer of this part. K q by 1 by r, 1 by small r minus 1 by capital R. Very important question, right? Note that potential of this is positive and outside is 0. So that means inner is always higher potential. Inner has higher potential than outer. If you connect them with a wire, current will flow, charges will flow from inner to outer. Right? Okay, let us move to the next. Question number 20. Let us solve this. Find the self energy of a uniformly charged self energy. What is that? Uniformly charged sphere of radius capital R. As shown in the figure, assume that the charge density is rho. Uniformly charged sphere. Volume charge distribution. It's like a insulator. Insulator. It is not a conductor. Okay. Conductor means it is like a cell. Okay. So now you think both cases. What will happen if it is a conductor? That means charge is only outside. What will happen in that case? What is self energy? And similarly, if the charge is only throughout the volume, what is self energy? What is self energy? Let us think about it. So first I will take a case, simple case. Here of course they have given uniform. Now let us take this case itself first. So we have charges distributed everywhere. Everywhere charges are distributed. So total charge is, let us say, q, and let us say that how do you build this sphere? So you are bringing some charges from infinity, 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 and you are building up. So what is the total work done? By external force is the potential energy stored in building this sphere. That is what is self energy. Okay, so self energy means the total energy invested in making this sphere. So how will you calculate that? So for that, let us say I was building, I was making it. So when I was making, let us say I have made a small solid sphere of radius small r. Okay, total radius is capital R. We'll see that. So this is a small. I have already made this solid, but now I am bringing a small charge, and I am trying to spread it over the surface to make it further bigger, like this. Okay, so already I had made a sphere, but we do not know charge. Let us say the charge I have spread here is a small q, and now I am bringing from infinity and putting a small q over its surface. Over, this is the process of building. Okay, small q charge is now made a small ball solid sphere, and a small dq charge is being spread over its surface uniformly to make the thickness little bit like that. Okay, so this radius is r, so this thickness is dr, right? Gradually you are building up to capital R. So while you are making this, what is the energy? So already you have made this solid sphere, small q. You are bringing, so this dq you are bringing from infinity. So what is the small work done? That charge into the potential V, V of this at the surface. So what will be that? V of the surface. So dq is the charge, but this dq you need to consider in terms of density. Density, let us calculate into, and this is the change of potential energy. We will integrate that. So dq, what you can write? You can write density, charge, volume charge density into this volume, which will be 4 pi r square dr into what is the potential of this? Potential formula will be what? What is potential? K Q KQ by R, KQ by R, right? KQ by R. Now, how can we write it? Now, how do we write this small q? Because we have already filled this. So, this small q will be again written as density into this volume, which will be small sphere 4 by 3 pi r cube. Yes, then we can integrate to 0 to capital R. We'll get the answer. Oh, let us do that. Can we do it fast? So try to do it fast. So rho 4 pi r square dr I'll put afterward. K also, k I can write 1 by 4 pi epsilon naught. What is big deal about that? This 1 by r is also there here. Q now I will write. Q is sigma, sorry, rho, then 4 by 3 pi r cube. What do you get now here? See, something will be cancelling out. 4 pi get cancelled. 1 r got cancelled. So what we are getting? Rho square has come out. Rho square has come out. Then what else? Rho square has come out. Epsilon naught will also come. 4 pi by 4 pi by 3 epsilon naught is also coming out, correct? 4 pi by 3 epsilon naught is also coming out. Now what are the powers of R? R3, R4 is coming, R4 is coming, and dr is also there. This is du. Now let us integrate. Integrate and let us quickly tell the answer. Yes, what will be the answer? Do it fast. What will be the answer? Can I do this here? Do it. So what will be the potential here? U. So r power 4 integration will be what? R power 5 by 5. Correct? R power 5 by 5 will come. So 4 pi by, here 5 will come. 5 into 3, 15 epsilon naught. What else? Rho square. Rho square. What else? Check that. R power 5 by 5. R power 5. Is this correct? But dimensionally it is not looking correct. What happened to the dimension? No. It is in terms of rho square, so it's correct. If you want to bring in terms of charge, better bring it charge in terms of charge. You can bring it in terms of charge. You want to bring it in terms of charge or in terms of rho. It depends on the question what they have given. If you have to bring in terms of capital Q, you can open this rho. You have to open it. Correct? There is no other way. Rho you have to. But this is the correct answer then. Otherwise, so 4 pi by 3 epsilon naught, and here r 5 by 5. So 5 has come. 5 into 3, 15 epsilon naught, 4 pi rho square. Right? 4 pi rho square, 15 epsilon naught r power. That is the answer. Self potential energy. You want to bring in terms of Q, bring it in terms of, let us do that. So 4 pi by 15 epsilon naught rho square r5. Do that. So 4 pi by 15 epsilon naught. Rho is what? Charge. Q by volume. So Q square by volume. Volume is what? 4 by 3 pi r cube. Again repeat 4 by 3 pi r cube, because it is square of that. Then r power 5. Now tell me what is. Now tell me what it is. This 4 pi get cancelled. This 3 now will get cancelled. Right? So it will be coming now as how much? 3q square. R5 will be going away. So here 5 into 4, 20. 20 will come. Correct? 1 pi will also come, I think. Correct? That pi will be there. So 4 pi into 5, 20 pi. 3 has gone up. R6 or R. This is what it is. This is the self potential energy of a solid sphere. We have derived it basically. Okay, so that's what. What about that small cell which I was talking about? For cell also derive. Is it very difficult? No. Cell like that. But cell means the same radius. Here radius you are not changing. You are just bringing charges to make it capital Q. So let us say right now charge is small q and you are bringing a small dq charge. So what is the small work done or change of potential energy is this dq into potential. So potential formula is k q by radius r. This integration is quite easy, right? Here it is quite easy because k q and 0 to capital Q you will go. So q square by 2r. Very good. 3 steps you have got it. Very nice. That is the self potential energy of a cell. This is self potential energy of a solid sphere, insulator sphere, right? That's one. Done. I think you have got the idea about how to solve questions. 20 questions we have discussed. You must have got a clear idea where can be confusion. All this confusion should be brought now. If it is not brought into discussion, then what it is? Simply solving questions like mug up is not the thing. Every thought process should be there in front of us. Then we can think which is right, which is wrong, which is right, which is wrong. Correct? That's very, very important, and you need to bring discussions like that, right? So thank you for your attention. We'll see in the next class.